Hi, this is Łukasz from EdgeDB and I badly need a haircut. It's been a while. You're watching the fourth episode of Import AsyncIO, an introduction to the Python framework enabling asynchronous single-threaded concurrent code using coroutines. This series is intended as a beginner's course. So if you haven't used AsyncIO yet, that's perfect. Just be sure to start at episode 1 if you haven't seen that yet. And if you have seen the three first episodes, yes, it's been a while. What we've been doing at EdgeDB is working on our Alpha 3 release. So I highly recommend you go and check that out. It's been a while since the last episode, so we'll make up for that by explaining how coroutines are implemented under the hood. We'll see how tasks and features build on them, and we'll spend quite a bit of time on the future objects in particular. So to build our understanding of coroutines, we need to first talk about what features are. Without knowing this important building block, it's hard to connect all the dots, and we didn't have time to play with them in the last episode, so we're gonna do it now. We'll learn about them from the user's perspective, and then we'll move on to explain their implementation. Equipped with this understanding, we'll briefly go back in time to Python 3.4 to see how AsyncIO initially was implemented and how coroutines looked like at the time, before async and await were added to the language. Then we can see how it all connects together in the task class. But fast forward to 2020, the implementation is no longer so straightforward, so we'll look at some of the gnarly C code that is used to implement coroutines natively in CPython today. Then we'll briefly look at the other coroutine-like types that you can create yourself, which can be awaited on. And finally, I'll mention the most common pitfall that you as viewers are complaining about and asking about how we can deal with that. So I wanted to address this in this very video. Sorry, I had to. What is a future? It is an object serving as a container for a result which we don't have yet, but hopefully we will in the future. So it's a standardized way for the producer of the return value to set the result or an exception if a result couldn't be computed. In turn, the viewer, the consumer of the value, also now has a standardized way to check if a result is available already and what it is. So both parties now can communicate using a kind of established protocol, and they can even cancel the future, essentially saying that they don't need or they cannot accept the result anymore. So let's see how that works in practice. A future object can report whether it's done or canceled. If we create a single one, we can ask it, are you done? False. Or are you canceled? False. So it's got a special method to get its result. But if we don't have the result set yet, it will raise an exception. So let's set a result. Result is set. Cool. Running that same set of methods, we'll see that it is in fact done as a future. It's not canceled. And the result is now available. So this is a pretty nice API that allows us to communicate future results between different parts of our program. Hopefully this API isn't really surprising. I do think that it is actually kind of standardized across languages. It's a very popular construct. Sometimes it's called the promise. In other languages or frameworks, it can be called the deferred. But it is pretty much, replicated across the board. It is very fundamental to what we're going to see next. So now, the cool thing about the futures in AsyncIO is that they can be awaited on just like coroutines. So here we create an async function, getResult, which simply awaits on the awaitable that we give it as its sole argument. So we assume that the returned value here will be a string. Let's just have this assumption, that's fine. We have some basic error handling, so if there is any exception during the await, we will return some dummy value instead and even have some print-based logging. So that's it for our function. So now creating the future object, we can tell an event loop to just after 10 seconds set the result on the future. That allows us to see what's going on, so that when we use run until complete with our getResult coroutine now, passing it the future, we'll see, in fact, it does return the result as we set it using the loop's call later scheduled callback. So, works as intended. Awesome. But if you look closely at our async function, it doesn't actually say future in the type annotation. It actually doesn't say future anywhere. So that's intentional. Thanks to the fact that futures can be awaited on seamlessly, we can compose them in powerful ways with other coroutines. To see this in practice, look, we can now wrap getResults multiple times and see if it still does what we want. Let's wait for a bit longer, like the 20 seconds is here. And now, instead of just running getResult, let's wrap 3 of those together. So having this, we're going to have to wait for a little longer while. I picked 20 seconds just so that you can see that in fact there are some waits involved here. So yeah, another result. We still got it, even though there was this matryoshka of calls right now. Pretty cool. Composes very well. We could see that the inner await was blocked on waiting for the future's result to be set. Now, if we are naughty and the future does not set a result, but we have an exception set instead, our getResult coroutine will handle it, right? You remember there was this try except block that was supposed to handle our exceptions. So instead of set result, let's use set exception right now and see what is going to happen with our run until complete call. We can just use a single getResult now. So waiting, we'll see, oh, our error handling in fact did kick in. Oops, problem encountered, no result, right? That's our fallback result that we've set in the implementation. Pretty cool. But wait, wasn't cancellation an exception as well? Let's see if that gets swallowed by our basic exception handling. So call later, in 10 seconds, we're only going to cancel the future instead. Running this, let's see if we swallowed this with, oh, we have not. The canceled error managed to propagate, so the cancellation works correctly. Why? Because starting with Python 3.8, canceled errors are now base exceptions, similar to keyboard interrupts. So this works around Pokemon exception handling breaking AsyncIO cancellations, which used to be a rather popular problem. So the Pokemon exception handling is a kind of meme term for every time where you decide to catch all exceptions and you don't really care about their type. This is rather flimsy as an error handling technique altogether, but thanks to making canceled error a base exception, now we are more resilient against this kind of flimsy programming. So the framework is ever evolving. Another thing I want to show you now is that a single future instance can be awaited on by multiple coroutines. Well, if we set a value, why not let multiple coroutines read it, right? It's fine. So we've already seen nested get result calls, but what if we ran multiple get result calls concurrently? We already know AsyncIO gather, so let's use that to run 3 of those at the same time. And in fact, turns out this is fine too. Futures allow for a surprisingly broad array of use cases. So finally, you can add callbacks directly to future objects, and they will be called when the future is done. Done doesn't necessarily mean the result was set, right? There's also the error case, but that means it's over, right? So there's a detail about how this works that is surprising to some users. So let's see this in practice. We are adding the done callback of the callback that we defined above, but I'm also doing another callback. In AsyncIO, you can schedule multiple callbacks on a single future. And in this example, we're just stopping the loop. It's kind of peculiar, but let's see why. So when you set the result, callbacks should be running, right? But they're not. Why not? So now we run the loop forever, and suddenly we see, oh, now the callbacks have been run. So it is a bit surprising, right? Like callbacks run on the event loop and not directly on the future when the result is set. But that's actually a good thing. Like they are now treated as any other AsyncIO callback if you register them with call soon or call later. So as soon as we run the event loop, the callbacks on the future registered, were invoked as expected. But wait, like how did the event loop know about our future and about the callbacks we registered on the future? So let's look under the hood. The implementation of futures is easily found in AsyncIO/futures.py. The future class holds most of the functionality. You can see in dunder init that it takes an optional loop argument. And in fact, if not given, it'll take the current one instead. Why does it need it? Oh, if you actually look at add done callback, it schedules the callback on the event loop that it set during dunder init. That's interesting. But what is even more interesting is that the act of setting the result actually has some logic there and then schedules callbacks to be run. So here again, the future is invoking loops call soon in line 243. We can see this happening. Well, why is this done like this? The reason why is so that now we are using fair scheduling. Doesn't matter how you schedule callbacks on the event loop, whether you're using call soon, call later, and friends, or you're using callbacks on futures. There's fair scheduling, first in, first out. That way, we are less likely to starve tasks from execution when there is a chain of futures that have callbacks on them. So that's a pretty interesting detail that sometimes people miss, and then there's confusion when they don't expect this kind of behavior. But all in all, I find it really elegant. So by this point, you are already familiar with coroutines, with futures and tasks as users, right? Like, that's pretty cool. We've seen how the future is in fact implemented just now. But what about the implementation of the coroutine itself? Sorry, I had to. So let's get back to 2014 when Python 3.4 got released. That's the version that first introduced AsyncIO as part of PEP 3156. That initial AsyncIO iteration didn't include async and await as keywords, so using AsyncIO was a bit more awkward back then. I built a Python 3.4.10 just to show you that in practice. So, from the user's perspective, instead of saying async def as we are right now, you had to use a decorator. So if we had a regular function that did some long-running computation that we always like to simulate with time sleep, the equivalent in async terms would be an @asyncIO.coroutine that now has a yield from asyncIO.sleep. That's peculiar. Why are we using yield again? Well, we'll get to that, don't worry. But for now, let's check if this even works. Let's start with running the regular function just to see that, expectedly it's slow, but it executes, right? Cool, return 0. So now there wasn't an asyncIO.run back then, so we have to grab the event loop and do run until complete on the async function, right? So we do just that. As expected, we have to also wait, and then we're getting 0 as a result. But at least now what we can do is we can use gather or whatever else to run many of those at the same time to get all values back without having to wait 3 times the time. So seeing that in practice, that is in fact what is happening. Cool. Boom. So if you look closely, the difference between regular function and async function isn't just the coroutine decorator, even though that's an important one. The fundamental difference is that async function here is a generator, right? It uses the yield keyword in its body. So Python recognizes this as a generator function and compiles it differently. So both regular function and async function objects are functions, right? However, calling async function reveals that it will return nothing more than, let's see, a generator instance. Cool. So let's review what that generator is then. So that will be important real soon. So you might know this already, that a generator is a special kind of function that yields values one by one. This can be used in many ways, the most basic of which is either iteration or directly calling the next built-in. Here we created a very simple generator that uses a counter variable and just yields a bunch of values until it's done. So creating a generator by calling the generator function, we see that it has some machinery, some interesting machinery inside, like it stores its frame. Even though it's not running yet, like there is a frame for its variables. It's empty right now. But as soon as we called the first next, now we have our locals in the frame. So running it a few more times, we will see that in fact, the code updates the variable. It behaves just as any other Python program, but it's interesting that there is this suspended execution until we run to the very end, right? Like once we call next when it's greater than 9, it will erase stop iteration, meaning I don't have anything else for you. I'm done. So now GI running will say false to us. Interesting. So if you immediately think like this is very similar to async functions with awaits, yeah, you're right. But you probably also noticed that AsyncIO in 3.4 was using yield from and not yield. What's that? So generators can access the full power of Python in their bodies, right? Like including iterating over more generators. Kids in my day would just quote exhibit and say like, I heard you like generators, so I put a generator in your generator so you can iterate while you iterate. And in fact, we're doing this in the outer iterator right here, yielding from the generator we defined above. You see, it works just fine when we run it in a for loop. And it works. But your question would probably be, hey, but I could just create another for loop inside that outer generator and be done with it much quicker and without having to learn of a new construct called yield from. So why bother with that? Turns out the humble yield from expression is an equivalent of almost 40 lines of code if you want to really correctly account for error handling and generator sends. For details about why this is necessary, I invite you to go read PEP 380. I already mentioned that one in the first episode of the video series. But for now, if you haven't heard of being able to send values into generators, this is where stuff gets interesting. The details are all in PEP 342, but for now, let's see an example redefining our generator with an inner counter that allows external users to change the value. See, the yield expression can return a value too. Most of the time it won't, so it will be none. But if it is not none, that means the user, the side that iterates, sent us a new value. So we're going to use that new value for iteration. So in practice, as you can already see right here, the generator behaves exactly as the previous one. But if you use the send method, which is a special form of next, so it also already does the next step of the generator, you can change the generator's behavior now, including causing early exit, right? We now moved past the rule that said, oh, we're exiting, we're no longer returning results. So that is actually the interesting part, that we can now communicate with a generator both ways. So what else is there? There is, in fact, a special method provided just to be able to cause an early exit, called close. There's also a more generic method to raise arbitrary exceptions, so not stop iteration, but anything, called throw. With all those building blocks now, a clever Python framework could use the fact that generators keep their frames around until they're exhausted, and treat those generators as cooperative functions, cooperative routines, coroutines. So after all this long introduction about generators, how did coroutines work in AsyncIO in 2014? Let's start here. What this is AsyncIO / coroutines py, and we are looking at the body of the decorator to mark coroutines. Like, this probably has some meat in here, right? That changes a regular generator into something really special. The font is a little small, but if you look closely, you'll see that the happy case is just 6 lines of code actually. Is this a generator? Yes, assign to Coro. Are we in debug mode? No, assign Coro to wrapper. Then put a magic underscore is coroutine attribute on the wrapper and return it. Done. That's disappointing, especially looking at the rest of the code. All the other lines are needed for special cases. Like, what if somebody used the coroutine decorator with a function that never yields inside, so it is a plain old function, not a generator function. So we deal with that in lines 139 to 144. And in the debug mode, we wrap the generator in an object that allows us to tell what generator we're dealing with. And that has some logging with an error message on unused coroutines. So that's pretty much it. That wasn't very interesting. It seems like in Python 3.4, coroutines are really regular generators. They're just marked with a special attribute, probably for some type safety reasons, right? So where is the magic that turns generators into pieces of cooperative multitasking? We've looked at coroutines py. We've looked at futures py before that. No dice. So let's try tasks py next. Support for coroutines, you say? That looks promising. And indeed, the docstring for the task class says a coroutine wrapped in a future. The class inherits from future, and indeed also in its init method uses a loop attribute as well. But what's that? Right in the dunder init method, we use a call soon on the loop. Interesting, with an underscore step. Let's see what that's doing. There's quite a bit of code here, but the most important piece is here, right? We're calling next on the Coro generator. So just a single step right here. And there's implementations of some exceptional conditions, like stop iteration, like cancellation, like other exceptions that can happen if there is an actual problem trying to compute the result. But in the end, you can see the meat is in the next of Coro. So when there is no exception happening, there's a lot of handling, and the most important piece here is another call soon call with underscore step scheduling itself back on the event loop. That is pretty interesting. It almost sounds like something we've seen before. So you've also seen that image before, mostly in the episode about the event loop. So just now we saw that the way coroutines work is indeed by just running callbacks. They just run a single step of their execution as every callback here on the event loop. And if there's any execution left, they use the trampoline pattern that you might remember from previous episodes to schedule themselves back on the event loop. So really what we will see is something like this. If there are many tasks, so many coroutines executing in the system, they will each have their steps executed one by one. In this particular example, the first execution of T1 underscore step scheduled itself back on the event loop. But before that happened, T2's underscore step was already scheduled. So it runs first, fair scheduling. Then we have another T1 underscore step and a new T3 underscore step. What happens later? Who knows? Maybe T1 and T2 are done, so only T3 is left and later more tasks. Or maybe they just continue going on, scheduling themselves back on the loop one by one. The most important thing here is to just realize that we just have a single thread of execution. So just a single callback being executed at a given time. But thanks to slicing all this code into small pieces, we achieve concurrency. So many things happen at the same time. Okay, I know this joke is ruined. But I needed this backdrop to let you know that we are moving back to Python 3.8.3, and we'll look at some modern AsyncIO code now. So first, let's look at some important changes in AsyncIO, the framework. Note that the task class is actually implemented in underscore AsyncIO. What's that? Oh, .so underscore AsyncIO. Those are typically hints that what we are dealing with is a C extension module. But there's still a Taskpy file. We just looked at it, and it links to the C implementation. But it also provides a pure Python implementation. So let's look at this code for a bit. So the Python task class in 2020 inherits from a Python future implementation. Not much changed, in fact, since we looked at the futures PY in Python 3.4. There is some new handling for things like context variables and some APIs that evolved over the years. But we still use the same trick with using the loop and scheduling ourselves on the event loop with a step. But now it's called a double underscore step. I guess this is to protect it from being destroyed by subclassing, which is now also supported. Cool. It actually works exactly as before, but now coroutines as constructs in the language have their own type. They don't have a dunder iter and dunder next, but we are using the send method of them to signify that stuff is happening. So the exception handling was exactly the same, and the trampoline pattern is still in place. We are putting ourselves back on the event loop after we are done with a single iteration. So that is interesting, but this is not the implementation that AsyncIO runs by default. As we can see, it imports _AsyncIO and just sets this as a task. So where does that live? This lives in modules _AsyncIO module.c. It's almost 4,000 lines of C, so if you're brave enough, no, I'm kidding. Just you can actually see for yourself that most of the code is a direct parallel of the Python version. In fact, the task step here is just a small wrapper around the task step implementation. If we click through it, we'll see that what is happening here, we need to kind of look through the boilerplate of C. We'll notice that, oh, we actually do have a send, and there is a throw like beneath it and whatnot. So it's still the same behavior as we just observed in the Python version. And in fact, more boilerplate, we will also be able to find our trampoline task call step soon. Pretty awesome, right? Looking at this thing, you can pretty much see that the implementations should stay in sync, but now we are using one that is way more efficient than during Python 3.4 times. So now, recap from previous videos. Async functions are regular functions, right? When we call them, what we get back is a coroutine. Instances of the coroutine type hold their state in special CR_ attributes. We've looked at the GI attributes for generators before, and we can still see a few very similar behaviors here, right? There's a CR frame, which is very similar to the GI frame we've seen before, and there's send and throw. As we've learned from the comment in Taskpy, there is no longer iter and next on coroutine objects, but we can pretty much achieve that same functionality using just send alone. So we're using this for coroutines. API looks decent. Let's see how this is implemented. So you might be a little surprised that the native coroutine implementation still lives in the same file where generators are implemented. So you'll find plenty of definitions. See that these are the attributes on the object, and we have our methods right below them. And if you look closely, you will notice that the three methods that we're using on native coroutine objects are in fact the native generator methods. So we don't even have to customize those. The default ones provide all the functionality we need. Now, I really want to drive the point home about how tasks run. The coroutines here are split into steps, but how much does a single step run? To see this, let's build an example async function that has a few awaits here and there, so we can actually test this in practice. We're starting with some simple example async function, takes a count argument, and let's say returns a string. So it's mandatory, like it's in the law. I have to use AsyncIO sleep. So let's use that right from the get-go. If count is 0, we return early, but if not, let's just have a loop, right? That loop can actually run another AsyncIO sleep for a while and then return some value. And that value, to be interesting, is awaiting another example call, just with a smaller count. This will enable us to test some recursion, or as you can call them, await chains, or yield from chains, as they're sometimes still called in the documentation. So to really see what's going on, we have to subclass the Python implementation of the task. This will enable us to wrap around the double underscore step to just create some logging before that step is invoked and after it's been invoked. You have to excuse me for hacking around the double underscore name mangling that Python is doing to protect private methods, but you gotta do what you gotta do. So as you can see, we do have the preamble that says, oh, we have a step on a task of a given name. Is it done? We're running that step, and after we've run it, we again say step is done, what name it has, and whether it's done. So to actually use this on an AsyncIO event loop, what you have to do is to use set task factory. It happens to have a different API than the task init method, which is a bit unfortunate, so we're using a helper lambda for this. Now, to really see what's going on inside that async function, it would be helpful to have more of those prints sprinkled before awaits and after awaits, right? Like, I know that print debugging isn't the thing, but in this particular example, like, we're gonna have nice output that we can analyze. So from this, I actually edited it so that we have this instead. It's the same function as before, it's just obfuscated by all those prints before the first await, after the first await, returning result, before await inside loop iteration, and so on. The point is, it will enable us to see how far a given step actually went before being done. So let's start with the simplest example that we can go with. If we put 0 in the count argument to example, we'll return early, right? With the if count equals 0 guard. So doing this, we actually see our nice logging, and there's already 2 steps. Interesting. We never recurse, but we can see the first orange step runs until the first await, and then there's a second step invocation, which runs from that await until the return. By the return, we can see that the task is done. Done equals true in the closing step log line. So things get significantly more interesting when we increase the count argument to our example. So let's do that. If we just put 1 instead, we already have twice the number of steps. The start looks almost the same, but because count is not 0, we are not returning early. In fact, we're already entering the for loop, and we're stopping at the await that is there. So that's step 1 and 2, but the interesting thing happens in step 3. So we see in step 3 that we are going past the await. Since that for loop was only 1 iteration, we are reporting after await inside and before await on example. But wait, the green thing on the left, step 3, also logs a line saying before first await, indented a bit more. Why? It turns out that Python already treated part of the await call with example as part of that single step. Already in that same third step, we ran the recursive example coroutine until its first await. Finally, the last step just keeps on running that recursive example coroutine until it itself, as the first example we've seen before, catches the guard. If count equals 0, we are returning. Let's look at this closely for a while, because this is something profound now, and even if we thought we understood what's going on before, that is really showing us everything step by step. So what's happening here is, for simplicity, you can just say a single step runs code until the next await expression. But there's more through this, right? As you can already see in step 3, AsyncIO already is recursing to our next example coroutine and runs that until the next await expression is found. Similarly, the final fourth step both finishes running the recursed example coroutine and returns from our outer example coroutine completing the task. Again, we see the completed task says done equals true on the last log line. So this is interesting. It seems that steps are really only stopped at actual I/O boundaries. That is something that we're not going to go into much more detail right now, but it already shows how Python is slicing computation step by step. Now, there's one more thing here that might be a little harder to notice. So know that there is only one task here the entire time. You see the log lines here, and it all says task 1, task 1, task 1, task 1. But we have 2 example coroutines. So why is that? This is because once we wrapped the outer coroutine in a task object, we already created this mechanism with a trampoline that enables us to just follow steps as they go. And execution inside can just follow regular generator-based computation. This is why PEP 380 is called delegating to a sub-generator. From AsyncIO's perspective, from the user's perspective, the inner coroutine's execution is just part of the outer coroutine's execution. Like we are pulling it one await at the time, looking at the very most await, right? So stopping only at await boundaries, you can think of it like this. A task object is the gateway to coroutine computation. This is where the trampoline pattern is used and where your computation is split into multiple discrete steps. Computation within a coroutine most often won't have its own wrapped task unless you create it using AsyncIO APIs. But other than that, we'll be just running coroutines all the way down. Finally, in real-world AsyncIO programs, there will always be more than a single task. In a web server, for example, you will have many of them handling different users' requests. And that's gonna all happen at the same time. So each one runs only a short amount of code before coming across an await, and then it schedules itself back on the event loop and yields execution back to it. So the event loop can choose to execute more callbacks, or it can react to I/O events, and so on. And this is how concurrency is achieved. For our final subject, let's go back to the beginning and look at the modern pure Python implementation of the future class. One interesting thing here is that now it supports a dunder await method. In fact, the dunder iter method is now simply an alias to dunder await. So users can still, for now, use the legacy yield from. So this is already a hint how you can create your own awaitable types. Custom awaitable types are not very common in user code. I want to show you this capability to complete the understanding of the 4 fundamental types in AsyncIO. But I'd be surprised if you were to implement your own type on your first big project. Like, probably not. But looking at the data model, which you probably should browse through anyway, like that's Python documentation, it explains things really well. The dunder await method must return an iterator. And that's pretty much it for the documentation here. So let's think of why this is a requirement. So coroutines are their own types right now. That's true. But they are still generators internally in a lot of their behavior, right? Like they share a lot of code. In fact, like the implementation of coroutines lives in genObject.c. So let's think of them as generators for a second. And let's think of yield from. So what does a generator do? It generates things, right? So very often in AsyncIO code, you don't just have one yield from, you will have a chain of them. We already saw a chain of awaits in our silly example with our example coroutine returning await example, so that it actually kind of nested, right? So that is typical to AsyncIO applications. But what does this generator generate? In fact, when you are calling iter or next on a generator, you expect to get an item. Like if not stop iteration, like you really need something. So at the very end of the chain, there cannot be just yield from all the way down. There's gotta be a yield. There's gotta be some termination of this chain so that at some point we are actually returning a thing. So, this is exactly why implementing dunder await, you are supposed to return an iterator that will yield a value. We've seen this in practice, like steps that are suspended on some actual I/O with AsyncIO. Right? Like we've seen steps being kind of arbitrarily broken into, and this is why this is happening. The break happens at the terminating yield. With custom awaitable objects, you need to return an iterator which terminates this, and the future already does this, but it returns itself. It's a kind of a special case. That's it. At this point, you have a thorough understanding of the building blocks behind AsyncIO. Like today, you learned about how coroutines are implemented in CPython and how futures and tasks build on this functionality to power AsyncIO, and how the step functionality uses the trampoline pattern to enable concurrent execution. Now for the requested thing. Like this was something that some of you mentioned in the comments on previous episodes. You'd like to know a bit about how to deal with this annoying problem that AsyncIO programmers encounter when they first learn the framework. We're gonna do a full episode on error handling, debugging, and testing. That's gonna be at the end of the series. But since this is such a common question, let's address the top gotcha right now. To do this, let's look at the text editor with our example coroutine again. If we just run it, you see I stripped our obfuscating prints from the coro, and now I stripped one of the awaits from the coroutine. Coroutine sleep was never awaited. That's something that Python will already tell us about, but it doesn't say where we made the mistake. If you said, you should always set Python AsyncIO debug when stuff is going wrong, but if you said Python trace malloc equals 1 at the same time, it will tell you where you forgot your await. So that's one particular case that is often kind of omitted. It is a source of grief and confusion. But there's even a worst one. If you actually use a return value, and that return value happens to not be awaited on, there is computation that happened. Python ran your code perfectly fine, but it returned a coroutine object instead of our result. But what's here? I'm using MyPy, and MyPy, through my type annotations on our async def, told me that, hey, you are doing something fishy here. The return value type is incompatible with what you said you're gonna be returning. So if you thought that the type annotations I've been putting all that time are just for decoration, think again. Like every now and again, there is an await that you're going to forget. And when that happens, most likely, at least Python will raise a warning. But if you're less lucky, it will execute your code until type errors happen a long way away from where your problem was actually introduced. So to fix that, use type checking. It will tell you exactly where you made your mistake. Finally, just as an excuse to show you my favorite illustration of the series once more, a comment about AsyncIO's performance. So what the event loop is doing with all our tasks is splitting them into tiny steps, right? And there's very many of those. The event loop itself is already some computation. We've seen how it works on a few weeks back in the first episode, right? There is a selector or a proactor that handle IO events. There are some collections that the event loop keeps internally for their own purposes for the callbacks, and so on and so on. So none of this is free. All of the computation that we're doing here has a price compared to regular synchronous code computation. So how come is this a model that is worthwhile and provides better performance in the end? Well, the reason why is that as soon as there is networking involved, the actual network latency between the server and the client is typically orders of magnitude higher than the computational cost of maintaining an event loop and splitting your coroutines into small steps. By that time, it is much more efficient to use this green threading or cooperative multitasking to make sure that you are able to use your single thread to its max capacity. You could just use regular threads. Again, they are not very easy or efficient in Python in many ways. So AsyncIO at least provides you with a more clear deal. And that clear deal, admittedly, is something that sometimes has some thorns on it. For example, if any of those steps ran for a long time, it holds up the entire event loop. So this is something you need to plan for, and you need to be able to discover when it happens. Blocking calls should not happen within async defs. Sometimes they will, you'll discover them, you'll fix it. So whenever you see big latency variation in your servers, typically there's some blocking computation happening there. Or there might be just regular Python computation that is never split with even a single await for a long time. But for regular web servers, for regular networking systems, because it's just not just web, obviously, AsyncIO will provide you with very nice capabilities to ensure that you maximize a single thread. And then you can run multiple copies to the number of the CPU cores you have on your machine. The operating system also is a scheduler, so you could not have all this and just run synchronous processes, right? Like maybe tens of them, and just let the operating system schedule them when they are waiting for I/O. Like, so why is that not better? Well, it's not better because each of those processes requires memory, especially with the garbage collection and reference counting we have in Python. Processes that we're using are not very copy on write friendly. They're gonna use quite a lot of memory. We're not particularly more hungry than any other runtime based programming language, but what I'm trying to say is that you can rather realistically handle thousands of clients in a single AsyncIO process at the same time. You're going to have issues running thousands of processes on even powerful boxes. So in that scenario, you're just getting a better bang for your buck using asynchronous programming, even though sometimes it's annoying because you're forgetting your awaits. Sure enough, now, having all this knowledge from the episodes so far, we can start building applications that are going to produce more exciting examples. Like, I hope we won't have to come back to asyncIO.sleep. Believe me, I'm as tired of it as you are. So what's next? Yet again, this particular episode turned out to be longer than I thought it would. There's more information in it than I thought I would put in a single episode. But that's nothing compared to what I'm planning for the next one. The ambitious goal for episode 5 is to introduce you to async context managers, async iterators, and async generators. Now that coroutines have their separate type in Python, AsyncIO can differentiate them from regular generators. So we can have asynchronous generators. They're actually very powerful. So we're going to be talking about them. And more importantly, we're also going to see some of the best of what AsyncIO has to offer as a library. So we'll be creating connections, servers, watching file descriptors, spawning sub-processes, which is one of my favorite APIs in Python, period, and using all sorts of synchronization primitives. You actually already know one. The future can be used as a synchronization primitive. So if you're now puzzled how, treat this as your homework. Try to figure out how you would use a future as a synchronization primitive in AsyncIO. In fact, what I would like to know from you is what is your favorite and your least favorite thing about async programming with AsyncIO, especially if you're new to this. Like, all this series is in fact done to teach you program in it, like to become comfortable with it. So your answers, like, put them in the comments, like, might inform our future episodes. Like, as this particular gotcha that we covered today, we can even make more drastic changes to our plan depending on what you find most valuable in our videos here. So subscribe to make sure you'll get notified when the episode is out, and I promise you won't have to wait a month for it. Thanks for watching. See you next time.